Okay folks, here we are back again with the third in our series of basic stress analysis with Ansys. So we're going to just take off from where we stopped with the last video. Okay, so here we go. We've solved our plate, and if you might remember, we had some problems with the stress in particular. So the Y stress was giving us a constant value of zero point 0.1 e to the 8 pascals, and the X component of stress, there's just some serious problems there which we're going to talk about in this particular video. Okay, let's just go back to the Y component of stress first of all. So we've applied a load in the Y direction, and we should have a constant value of stress in that direction, okay, because we have a simple plate and tension. So that's giving us a constant value of stress as we'd expect. But how do we know if the value we got is correct? Okay, so the first thing we have to remember is that stress is load over area. So we've applied a load of 1000 newtons. Okay, again, if we don't know how we've applied that, let's go and find out how we can do that. Before I do anything, I forgot to actually change my file name, remember? So the first thing I do, file, change job name, and this is number 3, so let's just change this to number 3 and just go save, just so we don't overwrite on the other files. Now let's go up to list and loads, forces on all nodes. So it tells us there's a force in the Y direction on node number 47 of 1000 newtons. Again, if I can't remember my dimensions I've put in, let's go list, key points, coordinates, so I can see that my coordinates of my square that I have here are basically 0, 0, and 0.1 and 0.1 of a meter, or is the other corner up here. Okay, again, if I can't remember what thickness I put on my elements, I can go list, properties, real constants. So there you can see I put in a real constant of 0.1 e to the minus 2, so that's my thickness. Okay, so putting all these values then together, let's go and calculate what the stress should be. Okay, so using our simple theory that stress is force over area, we can look at the dimensions of our plate. Our plate has a width of 0.1 meter. It's got a thickness or depth of 0.001 meters. So that means that the force, the area over which the force is applied, is 0.01 by 0.1, which gives us 0.0001 meters squared. So that is the area over which the force acts. Okay, our force is 1000 newtons. Stress is force divided by the area over which it acts, which is 1000 divided by 0.0001, which gives us 1 by 10 to the power of 7 pascals. So that's what our standard theory is predicting, that the stress should be in this plate under simple tension. 1 by 10 to the power of 7 pascals. Okay, so let's go back to Ansys and just see what that's telling us. It's telling us it's gotten a value of 0.1 by 10 to the power of 8 pascals, which is the same as 1 by 10 to the power of 7 pascals. So we now know we're getting the correct stress in the Y direction. So that gives us confidence that our model is accurate and is behaving as we'd expect it to. Okay, what about the other problem then? The stress in the X direction. Okay, so that's the Y direction stress is okay. X direction stress, what's going on here? Why have we got this? Again, we'd expect a constant value of stress here because this is a very simple problem. The reason we're not getting a constant value of stress is we've held one node down here in the X direction. We did that to stop the model moving around in the X direction, but now unfortunately we've created an artificial stress concentration at this one point here. Okay, so how can we get around this? The answer to this problem really is to exploit symmetry. Okay, so if you look at our problem, and let's just get it back up here again, let's get our elements back up. We've got a square, it's symmetric about the center here because we're applying a load on the center point, and this side is going to move towards the center, and this side is going to move into the center as the plate extends. So really we've got a symmetry line down along the point of load application here. So in order to remove that stress concentration, what we can do is we can remove one half of the plate, and we can tell the Ansys solver that there is a symmetry boundary condition here. Okay, so let's do that. So in order to do that, we have to clear our mesh. So we go into preprocessor, meshing, mesh tool, bring our mesh tool in. Let's clear that mesh. Okay. the couple set was deleted, the node that the boundary condition was applied to is deleted, so a lot of our information is gone. We're going to have to put that back in again. So again, we've got an area here now. So now what we want to do is divide that area in half. So what I'm going to do first of all is I'm going to move the work plane over into the middle of that area and divide the area by the work plane. So I go up here, work plane, offset work plane by increments, okay, and I get out here, I get this new menu up here. Let's just get rid of the mesh tool. Okay, so what do I want to do? I want to move the work plane along the x-axis. Okay, so I'm going to put in the value I want to move it along here, and I'm going to move it halfway along the width of the plate here. So the plate has a width of 0.1 meters, so I'm going to put in 0.05, and I'm just going to go plus x there. So you can see it's moved into the middle there. When we divide something by work plane, it always divides it along the xy axis, by the xy plane. So if I try to divide this at the moment, nothing would happen. So it's important that I rotate the work plane so that the xy plane is cutting through this plate in the direction I want to cut through it. So down here you can see the last time we used the top part of this menu. Now we're going to use the bottom part of this menu. So I'm going to turn up the rotation to 90 degrees, and I'm going to rotate around the y-axis. So I'm going to go plus y here. So now you can see that my xy plane is running in this direction here. So my z is now pointing this way, where previously it was pointing up towards me. Okay, so now I can divide the plate by work plane. To do that, I go to Modeling, Operate, Booleans, Divide, Area by work plane. Okay, so pick the area to be divided, this one, OK, and there we have it divided. Okay, so after I've done some things with the work plane, I may want to reuse that again later. In this case, I'm not going to, but in later, more complicated models, we will be doing that. So it's important to always put the work plane back where it was before you did all that. So in order to do that, we just go work plane and align work plane with global Cartesian. Okay, and just do a replot so you can see the work plane is back where it should be. So its x and y are pointing back the way they were originally. It's back in the global origin. We don't really need that work plane anymore, so let's turn it off. Work plane off. Now we're going to delete one half of the model, so we don't need this side, so let's delete that. So again, we go to Modeling, Delete, Area and Below. If we only picked areas here, then we would delete the area but keep the lines and key points underneath that area. Okay, in this case we don't want to keep the lines and key points, so we picked area and below, so everything below the area. Let's pick that area and go OK. So now it's gone. Okay, again, let's remesh this. Let's take a look at the lines. Okay, meshing, mesh tool, and we don't need this one anymore, so let's get rid of that. Mesh tool is out here, let's bring it in so we can see it. Let's set the line divisions again. So again, let's set these two to 10. And just to keep the same mesh as before, let's set these ones to 5. Okay, and then raise hidden, mesh, pick that one, okay. So there's our mesh. So now we need to rebuild our model. So let's do exactly what we had before. Let's first of all couple the nodes along the top here. So coupling, couple degrees of freedom, box is exactly the same as the last time. Go back to the other video if you forget how to do it. Okay, couple them in the y direction. Let's give them set number 99. Okay, and now we need to apply our load to one of those coupled nodes. So loads, apply, structural, force, on nodes. Let's pick this one in the center. Go OK. And again, it was a y direction load of 1000 newtons. Okay. Let's apply our boundary conditions. Same as before. Structural, displacement. We could put it on the nodes at the bottom or on the line. Let's put it on the line again. Let's put it on that line. And we only want to constrain that in the y direction. So okay. So now everything is the same as before, only we've got half the model. Here's what's new. We now want to tell Ansys that this is a symmetry line. So we apply symmetry boundary conditions on lines. Pick that line, OK, And you might be able to just see that little s's have just come up there. Okay, so if I just plot lines, maybe we can see that a bit better. Yeah, so there's S for symmetry boundary conditions on that line there. Okay, let's just solve that, see what happens this time. Again, same as before. If you can't remember how to do this, go back and look at the other previous tutorials. Okay, solution is done. General post-processor, always plot the deformed shape first of all, just to make sure everything's behaving as expected. Yeah, that's thinning in this direction. It's expanding in the vertical direction. Let's get a Y plot of stress. Okay, what's after happening here? We've got a constant stress, but we've got 200. Why did that happen? Okay, we'll come back to that in 1 second. And let's look at the X component of stress. Okay, again, so we still have problems in stress in the X direction. But the thing to do is to always look at the values, okay? So it's telling me the maximum stress here is 0.194 e to the minus 5, so that's really negligible stress. So again, we can see a range of a compressive stress of minus 0.5 e to the 6 and a maximum tensile stress of 0.19 e to the minus 5. So really, there's no stress in there. Okay, this has just been introduced due to some computational problems in the finite element method itself. Okay, and again, we'll come back to this later on. It's one of the reasons why you shouldn't always trust finite element results unless you can validate them. So the only method of validation we have at the moment is the direct stress in the Y direction, and that is looking okay. Okay, so we're pretty happy here in this case that these are negligible, that we can assume there's just a constant stress in there or no stress in that direction. Let's just go back and look at the Y component of stress. What's after happening? That was 0.1 the last time, and we determined that was correct. Why is that 0.2? Unfortunately, we put the force on the symmetry boundary condition. So basically, that force was applied twice, because what Ansys does when you put in a symmetry boundary condition here is it mirrors everything over into the other side. Okay, so it's also mirrored the load because that was there. So the load has been mirrored as well. So it's just something to be very, very careful. So in this case, we can reduce the load by 2. And again, we'll talk about doing that in subsequent analysis. Okay, so that's the end of this third tutorial. Again, we've introduced a couple of new concepts here. We've introduced validating your model with simple textbook analysis for direct stress. And we've also introduced the concept of symmetry and dividing your model using the working plane. Again, all of these concepts are covered in much more detail in my book, Practical Stress Analysis with Finite Elements. So if you're having trouble understanding any of these concepts, I really do suggest you get this book and take a look at it. It's written specifically for beginners. It's also written in such a way that it's not specific to any particular type of software. So even though we're looking at Ansys in these tutorials, if you're using a different software, it'll help you out there as well.